mechanism which is totally opposite to SN2. You have seen the contrast between SN2 and SN1. SN2 is a concerted mechanism, SN1 is a stepwise mechanism. SN2 depends upon first order with respect to substrates kinetically and first order with respect to nucleophile. But SN1 are first order with respect to substrate and zero order with respect to nucleophile, right? And stereochemically, SN2 reaction proceed via inversion in configuration, but SN1 proceed via racemization. You have seen the difference between the two terminologies in previous lecture. Secondly, the SN1 reactions, you are familiar with the classical carbocation and carbonium ion terminology is eliminated. It doesn't exist at all. So the ion which generates here carbon bonded with three atoms with the full positive charge is no longer cannot be called carbonium ion. This is against the IUPAC nomenclature. In fact, this is called carbocation. So carbocation you have seen normally you deal with the carbocation resonance stabilized. So that type of system is called classical carbocation. But there are certain carbocation, especially in the bicyclic, tricyclic, or polycyclic system where resonance stabilization doesn't exist, but the sigma electron pair stabilizes a positive charge. So this is in fact called as the non-classical carbocations. So you have come across these two different kind of the carbocations in previous lectures. So today we are focusing on SNI mechanism. This is a third kind of mechanism commonly called substitution nucleophilic intramolecular. So what is this? It was first studied by a few scientists that when we are having an alcohol is reacted with thionyl chloride. Thionyl chloride is the reagent here and the same is a solvent. So when it is going on in this case, look at the structure. What is happening in this case? Thionyl chloride undergo because it is just like carbon oxygen double bond. This carbon is electron deficient in carbonyl, commonly called COCl2, phosgene gas commonly called. But here it is not carbon, this is sulfur. This is a difference. This is called thionyl chloride. Keeping in mind, I have presented some bonds extraordinarily stable and some bond very unstable. I have presented if you have a fluorine silicon bond extraordinarily stable. The bond of sulfur with mercury, Hg, HGS bond. This is the extraordinarily stable bond. Extraordinary, very difficult to reverse or break this bond. But when we are making a sulfur bond with halogen or sulfur bond with nitrogen, they are very unstable bonds. Always. All halogen, including fluorine, chlorine, bromine, iodine, all of them have an unstable bond. Very similar if it is nitrogen, it is again unstable. But when sulfur make a bond with oxygen, this is extraordinary stable bonds. So anyhow, this is just to coach you here. So in this case, when this oxygen, which is having non-bonding electron pair acting as a nucleophile, this sulfur, you have seen already addition reaction. This is just like carbonyl addition. This electron pair transfer to oxygen, and this oxygen acting as a nucleophile donate electron pair to the sulfur, right? And once this oxygen is negatively charged, this is, if you remember, this is called tetrahedral mechanism. We shall see in this substitution reaction, in fact. This oxygen donate electron pair back and one Cl leaves. Cl leaves, it is overall substitution. First addition, second is elimination, overall giving you a substitution product. So what shall happen? This oxygen bonded here, making three bonds, this hydrogen shall be lost from here. So overall, one HCl molecule shall be the hydrogen from this oxygen and chlorine from sulfur. So it shall leave in the form of HCl. And this reaction is done in thionyl chloride as a solvent. This is a liquid in fact. So when this alcohol, either this is primary, this is secondary, but tertiary doesn't react, because if it is tertiary, this OH becomes typically much crowded, very poor reaction rate, so it doesn't undergo. We must have either primary carbon or a secondary carbon, then this reaction proceeds. So however, what it results, oxygen losing one H positive ion, this one, and chlorine from this sulfonyl chloride here kicks out, so results in the formation of this isomer. Now this bond of sulfur with oxygen, this is stable, but the bond of sulfur with chlorine is unstable. So what happens in this case? Very interesting. One of this oxygen takes this electron pair between this sulfur and oxygen and sulfur bond. This electron pair transfer there, this carbon become electron deficient, and then this chlorine takes this electron pair off from silicon. So this bond pair between chlorine and sulfur transfers to this carbon. You see, I haven't presented just simple arrow likewise. Why? Because this bond of chlorine with silicon, it is half, it is overlapping with this bond and showing this movement. This shows that both electron pair between chlorine and sulfur is transferring towards this carbon. This is called migration. You shall see this in molecular rearrangements. This is here, this chlorine is a migratory group, migrating from sulfur to carbon, right? So this is migrating there. So this carbon sulfur shall become electron deficient. This oxygen is taking this electron pair off, resulting in the loss of sulfur dioxide. And you see, within the molecule, the nucleophile is present. Chlorine with electron pair is transferring. What is the interesting feature in this case? Look at here, where the bond is cleaving from the same direction this chlorine is transferring. So this is what we call stereochemically, this is termed as retention in configuration. I have already presented this in previous lectures, that whenever you are having three bonds in same order, three bond, R1 is along the plane, R2 is also along the plane, hydrogen behind the plane, this group which lost, which is oxygen, so it was above the plane, and chlorine which points is also above the plane. So no change in configuration has been taken place here. That's why we call this retention in configuration. If you remember SN2, if I come back to this, yes, SN2 proceed with inversion in configuration that we commonly call Waldron. Look at here, the X group, leaving group is in this direction, and nucleophile is totally opposite direction, right? So X and Y are opposite. But if you compare this with SN1, this is entirely different. Where you are having a leaving group present at the same position, you are having a nucleophile present. So this is called retention in configuration. So later on, the scientists perform another very interesting experiment, because during this reaction, HCl was generated. So it can reverse the reaction. So that's why, because this can protonate this one. So if it can take this electron pair of Cl again reacting with it, resulting the same. So it was in equilibrium. So a scientist tried to uh, convert the reaction in forward direction. How? He tried to carry out adding a base. When base is added, base, nitrogen base, maybe triethylamine or pyridine. So when he used pyridine, in fact, he carried out this reaction in pyridine as a solvent. Why? Because once HCl is generated, it shall react with pyridine to form pyridinium chloride, a salt, which shall be precipitated out. So solution shall not be acidic in nature. So it shall not be reversed. So most it shall be proceeded in forward direction. So this was studied by a scientist. But when he studied the product obtained in sulfonyl chloride as a solvent, he obtained this compound and its optical rotation was different. And when he carried out this reaction in a base like pyridine or triethylamine, he observed entirely opposite optical sign. with same value. So what this indicates? This indicates that a different mechanism is being studied. So stereo, you see here, stereochemistry, or you can say the optical rotation is confirming here that mechanism is going different. Otherwise, it is very similar that it is undergoing this reaction. So this is just acting as a solvent. It will react with acid to form pyridinium chloride. This is the only role, but it means the different product is forming. If one enantiomer, it means if let's say this is dextrorotatory, this is dextrorotatory, but the product he obtained in pyridine as a solvent was levorotatory, it wasn't dextrorotatory. Both have same molecular formula. They have chlorine present in them. How we can check the chlorine? You have come across in previous semester how we can test them. If you remember lysine test solution, lysine test or sodium extract commonly called organic compound, we ignite with sodium metal which act as a reducing agent, converts chlorine into chloride ions. So these chloride ions, so we separate them in three portions, lysine test. One we test for nitrogen, one we test for sulfur, one we test for halogens. They shall give halogen test positive. If we are adding to one portion silver ion, silver nitrate, so they instantly react with silver chloride to form white precipitate. If you are getting white precipitate with lysine solution, adding addition of the silver ions, so it indicates that it is containing chlorine. So both of these products, 3 and 5, they were showing same chemical composition, mean they have chlorine present, but their optical rotation was opposite. One was dextro, other was levo. So this indicates that two enantiomers are forming in this reaction. So if we are doing a reaction in the presence of pyridine and in the absence of pyridine, so it gives totally different enantiomers. So, so what is the mechanism involved with pyridine? Look at here. First, it is the common that thionyl chloride reacts with the alcohol forms compound number 2. This compound 2 doesn't undergo this mechanism. If you look at here, it doesn't mean it is generated in a first in two steps. This one is basically, if you look at here, the first is the synthesis of substrate. This substrate is synthesized. Conversion of this into this is involving single step. This is also a concerted. The leaving group leaving with the same time and nucleophile is approaching same time. If you remember, this is the characteristic of SN2. Nucleophile approaching and leaving group leaving, making a half bond here, half bond here. So in transition state, you can draw the transition state in which this sulfur chlorine bond shall be half and this chlorine carbon bond shall be half. This carbon bond with oxygen shall be half, or you can say this bond shall be half. This bond is breaking, this bond is breaking, this shall be half, this shall be half. Two new bonds are forming. Sulfur, oxygen, double bond shall be indicated with a dotted line, chlorine carbon bond, dotted line. So two new bonds are forming, two old bonds are cleaving. So two bonds broken shall be with a different color. You can draw the other two different colors. So transition state is involved. It is a concerted mechanism, single step, just like SN2, right? So it is, but SN2 proceed with inversion in configuration that we call Walden inversion, but SNI mechanism proceeds with retention in configuration. This is the totally opposite. Both are uh, basically concerted mechanism, but kinetically, nucleophile is present within the molecule. That's why this is called intramolecular. Nucleophile is present within the molecule. So it doesn't have a nucleophile. So it is first order with respect to that. But it doesn't mean if it is first order with respect to substrate, so it is concerted. So it is, we cannot call this SN1 because SN1 we have already designated. It is two steps, stepwise mechanism. So, and that proceed via the generation of a carbocation. Here there is no generation of carbocation. All right. So this is a very important, entirely different mechanism, differing from SN1 to SN2. No carbocation is generated, it doesn't match SN1, although it is first order with respect to substrate. So it's kinetically, it is also first order. So it is also unimolecular, but it completes in single step. SN1 completes in two steps. That involves the generation of an intermediate which we will call carbocation. Here there is no generation of carbocation. Transition state is involved. So this is resembling with SN2, but in SN2 nucleophile is separate and substrate is separate. Here it is different. Nucleophile is present within the molecule. That's why it is not matching SN1. It is not matching with SN2. So it is in between both of them. That's why we call this SNI mechanism. And if this reaction is done in the presence of base or in the absence of base, it gives totally opposite enantiomers. This is what I have presented in a comparison between these two slides. So you can see the two different mechanisms. This is done. First of all, what is happening? The same entity, rather this chlorine enters inside because these are the solvent molecule very abundantly present. What it do? It adds to this sulfur oxygen double bond. Once it is synthesized compound number two, rather this reaction takes place. This base which is present, it donate electron pair to this sulfur. This oxygen takes electron pair off. It donates electron pair back and Cl is lost. So here you can see Cl is lost. Now, chlorine is not present within the molecule. Chlorine is not present within the molecule. Now, what is happening? You see, in first step, one chlorine atom lost. So this HCl was protonated with this one, generating chloride ion, salt with this. Another chloride ion is also generated, reacting again with the solvent molecule of pyridine or triethylamine, again forming a salt. All right. So two chloride ions are present per molecule of this. So one of the chloride ion approaches a totally opposite side to this one. The driving force is what? The positive charge on nitrogen. When nitrogen is making fourth bond, it is positively charged. It takes this electron pair off. I already presented sulfur nitrogen bond is also unstable. So I take this electron pair off to generate pyridine again. This sulfur became electron deficient. It takes this electron pair off. So carbon became electron deficient at the same time from totally opposite direction chloride ion approach. You see where leaving group is leaving and nucleophile is approaching. Here nucleophile is separate and substrate is separate. So that's why this is following SN2 mechanism. This is following inversion in configuration, which we commonly call Waldron inversion. So this same substrate, this month, this substrate is proceeding via SN2 mechanism if we are doing this reaction in the presence of pyridine or any other strong base. The same shall be proceeding with retention in configuration in the absence of a base. So this is the entirely different chemistry that we can observe in such cases. Like so, proceeding further. No, I am interested to discuss factors affecting sub SN reactions. Keeping in mind, we shall switch over to SN1 prime, SN2 prime, SNI prime, SN1CA, SN2CA, tetrahedral mechanism, TD mechanism, and similarly, we shall also come to neighboring group participation. But before that, this is very important to understand the factors which affect these three. SN1 prime and SN1, so they are competing with each. Substrate is different only, but factors shall be the same. And similarly, SN2 and SN2 prime, so factors are all the same. So anyhow, you shall see that later SN1 prime, SN2 prime, SNI prime, all right. And similarly, SN1CA, SN2CA, neighboring group participation or enchimeric assistant and TD mechanism, etc. Later, I am just interested to show the factors which affect SN reactions. So there are various factors. I have highlighted a few of them here. The nature of the living group. Which group is living? If it is a good living group, the reaction shall proceed in forward direction, right? Nature of the nucleophile. How strong is a nucleophile? If the nucleophile is strong, it shall favor SN2 mechanism. If nucleophile is a weak nucleophile, then it shall favor SN1 reaction. You shall see that later. Polarity of solvent also affect the reaction. Mean if we are doing a reaction in polar solvent like in water or in methanol, so what we get? We get an entirely different product. SN1 reactions are favored. And in low polar solvent like in diethyl ether, we are performing THF, then SN2 reaction is favored. And so polarity of solvent is also very important. I shall exemplify this with examples. And static factor. Static factor is what it means. The crowding of steady crowding around a group, so it also make a big difference. So if there is more steady crowding around the carbon, so it shall favor SN1 mechanism. If there is less steady crowding, it shall favor SN2 mechanism. So anyhow, and similarly, the stability of carbocation, you have already come across about the carbocation. Its stability is also very important. If it is a stable carbocation, then it shall favor SN1 mechanism. If it is unstable carbocation, then it shall favor SN1 mechanism. So we shall discuss that one by one, starting from the nature of the living group first. But we have almost remaining 1 minute, so we shall log in again.